Okay, so this is a thermo problem from 2016. It's number 1. So we have 2 moles of this ideal gas in a cylinder with a movable piston. And then the gas is taken through this cycle. So as I always say, for these problems, you want to think about a gas in a cylinder like this with this piston that can move up and down without friction. Now, really important to talk about before we get into the problem, because we're going to need to know this, this idea of internal energy, which has the symbol U. Okay, so what internal energy is? Internal energy is it's the total energy of the molecules of the gas. So internal energy can be summarized as the kinetic energy of the molecules plus the potential energy of the molecules. However, potential energy, when you talk about potential energy of gas molecules, you're talking about a change of energy that occurs during a phase change. So if this gas is not undergoing a phase change to towards a liquid, any change of internal energy is going to be the result of kinetic. So we can pretty much ignore potential energy. I mean, if you were to so if you were to graph out temperature as you heated up a substance, so let's say you start with like a block of ice. So say we're doing this for water. The 2 important temperatures would be 0 and 100. So you start adding heat energy. So this would be heat added here. So you start adding heat energy, and when you reach 0 degrees Celsius, you're going to undergo a phase change where temperature is constant. And then when all of the substance has melted, when all the water is melted to liquid, you're going to get a temperature rise. And then again at 100 degrees Celsius, you're going to have a phase change. And then when all of it has converted to gas, the temperature goes up. So this is just your typical phase diagram. So this is solid, solid plus liquid, liquid, liquid plus gas, and then gas. So to relate it to this equation, anytime the temperature is changing, that's going to be from a change of the kinetic energy of the molecules. Whereas during a phase change, it's potential energy. So temperature change is, so wherever the temperature changes, that's kinetic. Phase change is potential. For this problem we're dealing with, it's always going to be a gas. So we can ignore potential energy. So any change of internal energy is going to be the result of a change of kinetic. That's a really super, super important idea. And then another equation we need to talk about is, how do you actually change the internal energy? You change internal energy by doing one of 2 things on the gas. You can either do work on or by the gas, so work is one, or you could add or remove thermal energy. So the internal energy of a gas is changed by doing either work or adding or removing heat or thermal energy. So this equation is very important. And let me back up to this first equation. One thing I want to say about kinetic energy, you should know the definition of kinetic energy is it's a measure. Let's see. No, I'm saying this backwards. Temperature is a measure. It's a measure of the average kinetic energy of the molecules in a substance. So kinetic energy is linked to temperature. If temperature changes, that means kinetic changed, which means therefore internal energy changed. And then there are other important equations. Calculating work Work can be calculated by taking the pressure of the gas and multiplying by the change of volume. I won't do it here, but this equation ultimately comes from the basic definition of work, which is work equals force times distance. You can derive that equation from this equation. So we're going to be using this equation for work. So if the gas pushes up on the piston, exerts a force on the piston, moving the piston a distance d, we would say that the gas did work. And then the last equation we're going to need for this problem, and this is on the equation sheet. I don't think many kids would have this memorized, but for calculating the kinetic energy of a single molecule of a gas. So let's say that this little dot right here represents a molecule of gas. To calculate that the kinetic energy of a single molecule, we go 3/2 Boltzmann constant, which is on the equation sheet, multiplied by temperature. And then last but not least, we are of course going to be using the ideal gas law to figure out temperature stuff, which is PV equals nRT. So this is kind of the background info of what you're going to need for this problem. So let's just start the problem. Okay, so the first question is calculate the force that the gas exerts on the piston at state A. So here is our gas, here's the piston. The gas is exerting a force on the piston. So to answer this first question, we're going to use the definition of pressure. Pressure is force over area. Metric units, force is Newton. Area is meter squared. A Newton per meter squared is what we call a Pascal, which is what we have here. The graph is given in units of Pascal. It's nice and metric. So solving for force is going to be pressure times area. So the pressure at point A is 1 times 10 to the 5th. So that's 100,000 pascals, which is a Newton per meter squared. And then the area is given right here, 5 times 10 to the negative 3 meter squared. Meter squared cancels. The force on the piston at point A comes out as 500 newtons. And then they also want an explanation. It says here, explain how the collisions of the gas atoms with the piston allow the gas to exert a force on the piston. So you definitely, for this underlined part, you definitely want to mention something about Newton's third law. You know, every force has an equal and opposite force. So if you imagine, you know, if this is the piston right here, if there's the piston and then here comes the gas molecule. So this gas molecule is going to have a velocity, comes in, it's going to bounce off of the piston, and then it's going to head this way. So this is V initial, and then this is V final. A really cool thing to recognize here is that the change of velocity, you know, if we say that this way is X and this way is Y, the change of velocity happens in the Y direction only, because if we break these velocities into their components, V initial has a X component and a Y component, and V final also has a X component and a Y component. Notice that the X components did not change. There was no change in velocity in the X direction. The change in velocity occurred in the Y direction. So our change of velocity is this way. And if the change of velocity is that way, the acceleration is also going to be that way, because change of velocity is acceleration. And we know, of course, that F net equals ma. So the net force is going to equal, the net force is going to be in the same direction as the acceleration. So if the molecule bounces off the piston, and if the molecule experiences this change of velocity and therefore an acceleration, it's also going to have a force in that direction. So that would represent force. And if the molecule has a force downward, that means that there must be an equal and opposite force that is upward on the piston, according to Newton's third law. Okay, let's go to the second question. So we're calculating temperature here. This is really quick and easy. So we're going to use, so for this one here, we're going to use the ideal gas law. We're going to go PV equals nRT, solving for temperature. That's PV over nR. Really, the only thing you got to be careful with here are the units. There are two versions of the gas constant. Make sure you're using the correct version. So we want temperature at state B. So pressure at B is 10 to the 5th pascals. And again, a pascal is a Newton per meter squared. Volume at point B is 0.1 cubic meters. So our units are looking good. We got meter squared, cubic meter. We have 2 moles. N is moles. So number of moles is 2. And the gas constant we want to use is the metric version, which is 8.31. That's going to be cubic meter pascal over mole Kelvin. If you look this up on the College Board equation sheet, you're actually going to see this as a joule. A joule is equivalent to a cubic meter times a pascal. But now the units all cancel out. Everything works out great. And we get a temperature of 601.7 Kelvin. Now, we're going to need temperatures at other points as well. Coming up for the next part, and I've calculated these already, but doing it exactly the way I've done here. So let's just label all our temperatures. We're going to revert this. So we know at point B, the temperature at point B, we calculated it to be 601.7 Kelvin. And then I went ahead and I also calculated temperature at point C, which was 300.8. And then the temperature at A is 240.7. We're going to need those temperatures. Okay, moving on to part B. Predict qualitatively, so we don't need to do any calculation. We're going to explain our answer, but not numerically. Predict qualitatively how the internal energy of the gas changes from A to B. Okay, so as I said earlier, so internal energy, any change of internal energy where U is internal energy, it's going to be equal to a change of kinetic. And kinetic is linked to temperature. If temperature changes, kinetic changes. And if kinetic changes, then internal energy changes. So here's the thought process. From A to B, there is a temperature increase, right? From A to B, the temperature goes up. And a quick way to show that, say you didn't have those temperatures there, from A to B, you could just go like this. So write down the ideal gas law, PV equals nRT. From A to B, circle what stays constant. Pressure is constant, moles are constant, R is constant. So what's happening from A to B? There is an increase in volume and therefore an increase in temperature. If temperature goes up, that means that kinetic energy goes up. And if kinetic energy goes up, internal energy goes up. So that's the answer to this question. So justify your prediction. You say from A to B, there's an increase in temperature. An increase in temperature leads to an increase in kinetic energy, and an increase in kinetic energy is an increase in internal energy. All right, next part. Calculate the energy added to the gas by heating. So this is, I think this is the trickiest part of the whole problem. B part 2. So let me make some room, get rid of that. Okay, so to do this question here, I need my pen back. Okay, so to do this question here, we're going to use the equation kinetic of a single molecule equals 3/2 the Boltzmann constant times temperature. Okay, so we're focusing on A, calculate from A to B. Now, first thing we should do, so we're going to go, okay, we want, wait, hold on. Oh, no, I'm sorry. We're doing this one right here. We're going from A to C. From A to C, we want the energy added to the gas by heat. Okay, so change of internal energy is equal to work done plus heat added or removed. So this is going to be important right here. Now, what is the total work from A to C? What is the total work done from A to C? Well, let's go step by step. So from A to B, we can calculate what the work is. So the way we find the work from A to B is we're going to go work equals pressure times change of volume. So essentially, we're calculating the area under the line segment AB. We want all of this. That would be the area under that graph is going to be the work done from A to B. If you would have calculated the area just inside the triangle, what that would have been is the net work for the whole system, for the whole cycle. Okay, so here's the calculation. So the pressure from A to B is 10 to the 5th pascals. The change in volume from A to B from 0.04 to 0.1, the change of volume is 0.06 cubic meters. So this gives a work of 6,000 joules, which is negative. We want to make that negative. And the reason why we make that negative is the volume is increasing, which means the piston is going up. And that means that the gas is doing work on the surroundings. So this is going to lead to a decrease of internal energy. An increase in volume, piston moving up, is considered to be negative work. So we know that this work here is negative 6,000 joules. The Q is a question mark. We don't know what the heat energy involved there is. Now let's go to BC. For this line segment here, the work is going to be 0. And the reason I know that is because there's no change of volume. If you look at this equation, work equals pressure times change of volume. From B to C, the volume is held constant, so there is no change of volume, so therefore no work. And then Q again, heat is a question mark. Now the thing to realize, this question wants the energy from heating. We want Q, but we want these two Qs together. This Q plus this Q together, right? Not separately, and that definitely makes it a lot easier. So we want total heat energy from A to C. So we already know the work, so let's take this equation and rearrange it. So Q is going to equal the change of internal energy minus the work, and we already know, so this is going to be change of internal energy minus the work, and we know that the work is negative 6,000. So basically, the thermal energy or heat is going to be whatever the change of internal energy is plus 6,000. Now, how do we find this change of internal energy? To find this change of internal energy, what we need to do is use this equation, because remember, change of internal energy is equal to the change of kinetic energy. So we're going to go to point A first. So let's start at point A. What is the kinetic energy of a single molecule at point A? So we're going to go 3/2 Boltzmann constant times temperature. So the kinetic energy of a single molecule at point A, it's going to be 3/2. Now the Boltzmann constant is 1.38 times 10 to the negative, where is it? 23. And that's joule per Kelvin. Temperature at point A is 240.7. So Kelvin cancels, and we find out that the kinetic energy of a single molecule at point A is 4.98 times 10 to the negative 21 joules. Okay, that's for a single molecule. Let's go to point C now. Let's do the exact same thing for point C. The only thing that changes is the temperature. So I'm not going to do this again just for sake of time. Just change the temperature now to 300.8, and we're going to get a kinetic energy of 6.23 times 10 to the negative 21 joules. So we definitely had a change of kinetic energy. And again, that change of kinetic energy is the change of internal energy. So the change of kinetic energy comes out as negative 1.25 times 10 to the negative 21. All I did is I subtracted these two, right? So this is basically our final. This is our initial. So change is going to be final minus initial. Oh, wait, no. This is positive. There was an increase. Temperature went up. So we're going final. This is bigger than that. So there's an increase in kinetic energy. Now, this number right here, again, this is for a single molecule. Well, how many molecules do we have? Well, there's 2 moles. So 2 moles, how many molecules are 2 moles? 1 mole is 6.022 times 10 to the 23rd. So our total number of molecules, let's just call it N. 2 times 6.022 times 10 to the 23rd. So we have to multiply this by 2 times 6.022 times 10 to the 23rd. And that gives us 1,505 joules. So the kinetic energy went up by 1,505. So let's bring that back up here. The thermal energy added is going to be, Q equals 1,000, basically 1,500 plus 6,000 gives 7,500. The thermal energy is 7,500. And again, just before we move on to the next question, like the reason why this makes sense is come up to this equation. Change of internal energy is work plus heat. So we know that the change of internal energy was plus 1,500. We figured out that the work from A to C was negative 6,000. So in order for this equation to hold true, the thermal energy has to be 7,500. Okay. All right, part C, the last part. Determine the change of total kinetic energy of the gas atoms as the gas goes from C to A. So now that we've done all this work in part B, part C is really not bad at all. But we are going to need temperatures again. So temperature at C was 300.8 Kelvin. Temperature at A was 240.7 Kelvin. So we want the change in the total kinetic energy from C to A. So we're going to start at point C, calculate the kinetic energy, 3/2 Boltzmann constant times temperature. You plug into that, and we get, at point C, we get 6.23 times 10 to the negative 21 joules. And then go to point A, we get kinetic 4.98 times 10 to the negative 21. So the change of kinetic energy, so we're going to go final. So let's see, we're going from C to A. So A is actually the final. C was the initial. So final minus initial, this comes out negative. This comes out as negative 1.25 times 10 to the negative 21 joules. But again, that is for a single molecule. So you have to multiply this by the number of molecules, which gives us 1,500 negative.